Life is too short to work at a crappy company. That's why Software Engineering Daily is proud to be sponsored by Hired.com, the job marketplace for software engineers. If you accept a job through Hired, they will give you a $2,000 bonus. But as an extra bonus to our listeners, you can get an additional $2,000. That's $4,000 total if you sign up by going to softwareengineeringdaily.com and using the link on the right side of the page to sign up. Hired.com will set you up with 5 great companies for interviews. These are companies like Stripe, Facebook, Uber, companies you would actually want to work for, where you can go and learn the cutting edge of software engineering. Go to softwareengineeringdaily.com, click on the banner on the right, and try out Hired.com. Several open source streaming platforms have appeared in recent years, and it can be difficult to figure out the trade-offs between them. Spark, Storm, Flink, and Samza each have benefits and disadvantages. Satish Mittal is an architect at InMobi, a mobile advertising platform that recently built streaming into its backend. Satish, welcome to Software Engineering Daily.
Thank you.
You work at InMobi, and in order to understand the backend requirements for your application stack so we can get an idea of which streaming platform was the best fit, could you tell me what InMobi does?
Sure. So I'll just give a quick introduction about InMobi. So basically, InMobi is essentially an ad network. And InMobi, as of today, it is able to reach around 175 countries and serve ad requests to the tune of around 8 to 10 billion daily requests. And it can also reach around 1.4 billion devices across the world. So as you can very well see, we essentially have a huge amount of data getting processed, and we need to make sense out of the data, gather insights so as to be able to serve the most relevant ads to the most to the user by giving him maximum value.
Right.
So that's the major premise of our processing. Yeah.
Yeah, and so for people who aren't familiar with the levels of throughput in these advertising technology platforms, I think a good analogy is like a stock exchange where you just have like tons and tons of feeds that are intersecting and matching buyers and sellers. There's a lot of data, and latency is a big deal. So
right. So yeah, that's a good analogy. Basically, an ad network is, think of it like a marketplace. You have demand and you have supply. So the in essence, we get requests from a publisher. For example, if you are on a mobile and you're playing a game, Subway Surfer, for example, and you see all those ads, so those are served by ad networks. And then there are a lot of advertisers who want to reach to their target audiences. They could be people who are using iOS, or people who are living in, let's say, US, or young people, college goers. There could be a lot of such criteria which they want to target. So,
and so in the past, we've done several shows about stream processing, and we've talked about this explosion of new technologies kind of that have come since the Hadoop stack originated. And the Hadoop was kind of this batch, everything is batch. But with streaming, you have different platforms and different sets of requirements with stream processing. So could you start off by defining what is real-time stream processing?
Sure. So as you have said, so far the big data processing inevitably meant batch processing. What it meant was there is huge amount of data getting generated by machines, and we have to just process that maybe once in a day or on an hourly basis, and what we care is to process the entire data. So we are mostly caring about the throughput, that hey, I have these hundreds of gigabytes of data or potentially terabytes of data. Can I crunch it as fast as possible in the chosen frequency? So typically batch processing would not care that much about latency, right? It would care about throughput. So that was the major trade-off. Whereas when we say real time, right? So the focus is more on how fast can I uh, get the required insight out of my processing. So basically, we don't want to wait for those hours or days to get to know that, hey, you know what, some activity happened in that part of the world on our network, but my ad serving systems are learning about it only the next day. That's simply not acceptable. So to define what real time means, we are talking about insights being available in a very short time interval. So we are talking, when we say short, we're talking of order of, let's say, seconds.
Right. So prior to implementing streaming, when you had this, when you wanted to get to this closer to this like second latency, many of your applications had to model themselves on micro batching, which is something you did with Hadoop. What is micro batching, and what are the problems with micro batching?
Yeah. So basically Hadoop was meant for doing batch processing, that hey, I have this finite data set, okay, which is getting generated once in a day. Okay, I have, let's take an example. I have these 100,000 files on SDFS which gets generated once in a day. Now if I were to reduce the latency on this very same platform, one obvious approach would be that, hey, why don't I reduce the size of my batch? So what it could mean is that, okay, why don't I organize my data in, let's say, some minutely directories, okay? And why don't I pick up 1 minute directory dataset at a time? So what I have done in this process is to shrink my batch interval from, in our example, 1 day or 1 hour to 1 minute. So basically we have broken up a huge batch into large number of small batches. Each such batch can be thought of as a micro batch. So this strategy works. It obviously gives us better latency than the last time. But then what happens to the underlying platform? Now Hadoop platform uh, sees a huge stress, because what happens is that we are submitting a very large number of short-lived jobs, and all these jobs are getting queued in my job tracker, and creating a huge stress on the processing layer in terms of the containers being asked. So for each job, for those who use Hadoop, they know that for each job there is a initialization time where the container has to be asked by your from your resource manager in the Yarn world. There is a setup time, there is an initialization time. So there is a lot of overhead before the actual processing can trigger in for the first message. Okay, so the problem is essentially happening because Hadoop is natively not built to perform stream processing. It's kind of a hack or kind of a workaround which we are trying to achieve by doing micro batching on Hadoop. And that's precisely the reason we need to look out for the best fit for handling such kind of use cases beyond Hadoop.
So now that we've motivated the need to move beyond batch and micro batch and towards streaming, let's talk about the different stream platforms that you are considering. At the beginning of your analysis of these different stream processing platforms, when you're looking at the different uses that you could, the different products that you could be using for streaming, what were these different streaming products that you were considering?
Right. So InMobi, we when we started doing our analysis for choosing the right stream processing platform, there were a lot of choices available at that time. It was so we were talking of around 6 to 7 months ago, and primarily we have Apache Storm, which is one of the first platforms to be built in the real time stream processing paradigm. And then Spark is these days getting a lot of traction in the batch processing. It has essentially replaced Hadoop, and they also have an offering in the stream processing world in the form of Spark streaming. So, given the large community of Spark and a lot of other advantages which you get, Spark streaming was yet another candidate we had. Then, in addition, we also were exploring Samza, Apache Samza, which has been developed at LinkedIn and later incubated into Apache. And last but not least, there was also Apache Flink, which had got incubated at that time, but it was a fairly new player. So basically, we just thought of picking up top 2 or 3 platforms, and we just narrowed down to Storm and Spark streaming. The reason for choosing these two was purely in the interest of time, because what we felt is that if one were to do justice to the evaluation, we need to first of all clearly define what do we really want. As an enterprise who wants to standardize on a streaming platform, there are some clear-cut criterias on which each platform has to uh, get evaluated and answer the questions. Doesn't matter whether the enterprise is InMobi or some other company, but these use cases and these asks are fairly common. So we thought of defining these criteria and then evaluating the platform of our choice on those criteria. So that was how we went about.
So you narrowed down your options to Storm and Spark streaming. You eliminated Samza and Flink. It sounds like you eliminated Flink quickly because it was just too young. Why did you eliminate Samza so quickly?
Yeah, Flink was really providing a lot of promising data models in terms of the DSL, but yeah, because it had just arrived at the scene at that point of time, we really didn't have the confidence. But Samza was an interesting case because there were in fact a lot of people who wanted to even explore Samza. So the things boil down for us to pick and choose between Spark streaming and Samza. So we just opened the forum to all the people, all the developers and architects, and we just sort of got a sense that probably we wanted to evaluate more Spark streaming simply for the reason that Spark is already being used by us in production.
Oh.
And there are already a lot of jobs running, and we are seeing good benefits. So there was a natural inquisitiveness or expectations to why don't we use Spark streaming. Samza, simply because we were not using, probably it was not finding those number of people favoring, but nothing to take away from Samza. It is indeed a great platform, but just as we said earlier, purely in the interest of time, we just wanted to make sure that this doesn't become a never-ending evaluation. So we just
Yeah. So You mentioned that Spark is replacing Hadoop. What do you mean by that?
Right. So when we say Spark is replacing Hadoop, that applies to the batch world. So
So are you talking about Hadoop MapReduce specifically?
right. So Hadoop was the de facto standard batch processing platform for a long time until Spark arrived, and Spark basically proved that there are a lot of performance enhancements slash benefits which are possible by an orders of magnitude over Hadoop, and at the same time maintaining providing a very simple interface for developers to be able to quickly code up their bash processing in terms of functional primitives. So there is no doubt that the big data future seems to be more aligned towards Spark.
Is the primary problem with Hadoop MapReduce that it checkpoints to disk so aggressively?
Mm-hmm. Right. That's one of the top reasons that Hadoop basically hits the disk, churns the disk more too often than probably what is needed. So in Hadoop world, each job can be thought of as a DAG or a directed acyclic graph of only two levels, where the first level is your map and the second level of nodes are your reducers. If you want any subsequent level, you have to first write the data to disk, then you have to trigger the next job which will read that the last output as its new input, and then again repeat the process, and this goes on and on. Now imagine if you were to run a machine learning kind of processing which is essentially iterative in nature, where you just finish a loop, get some intermediate output, again you want to run the very same computation. The time taken and the disk resources and the overall grid resources consumed are far too much. So Spark naturally wins in such kind of use cases in the batch world.
So if you're thinking already of the future being a world in which Spark replaces Hadoop MapReduce, why wouldn't you just go ahead and say, well, we might as well use Spark for our entire stream processing platform?
Yeah, there is a catch here. That Spark is basically, at heart, it's a batch processing platform. It is not natively a stream processing platform. So let us try to define what do we expect from a stream processing platform. So that and that's where the crux of our evaluation really lies. So the stream processing platform has to be able to support various kind of use cases. More so, if you want to standardize it as a platform in a large company where there are a lot of teams trying out various applications, some of them would say that, hey, you know what, I have this fire hose of event. As soon as I get an event, I just want to trigger my computational logic. I just want to quickly get the output and consume. I don't want to wait for it to be picked up with another batch of messages, right? So if we can generalize this kind of ask, it boils down to very low latency ask, where essentially an application wants an event driven processing. Okay, then there is another class of application which would say that you know what, we don't really care that much about microseconds latency. We are probably fine with hundreds of millisecond latency or even seconds of latency, but we do want a better throughput. And then finally the other extreme would say, okay, we are fine with tens of seconds of latency, but then we want even better throughput. So as you can very well see, there is a spectrum of use cases. Now, what we found out as part of our evaluation by going deep into the architecture of Spark and Storm is that they are clearly there is a lot of difference in what they can do and what they can't do.
Well, so let's start delving into those. Give me a high level overview of Storm's architecture.
Right. So Storm is basically uh, 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 DAG processing platform where it allows you.
That's directed acyclic graph for people who don't know.
That's right. By DAG, we mean a directed acyclic graph where you can represent your stream processing in terms of spout. So Storm would define some key terminologies where there's something called a topology which captures the entire graph, and the root of the graph would be what is called as spouts. So spouts are your sources of data which are ingesting data in your stream processing Storm topology, and a spout basically consumes input streams. Okay, a stream is defined as an infinite sequence of tuples. Each tuple can be thought of as a message, and tuples can be associated with schemas, and there are like primitive schemas, and you can define your own custom schemas through serializers. So essentially, spouts are the ones which would be ingesting data. So there could be like, let's say, Kafka spout. So if somebody wants to consume data from a messaging platform, messaging system like Kafka, so you can write a Kafka spout, or you can use the one which is available off the shelf. And then for each message, you probably want to trigger your own processing where your actual application code resides. So that is written in what is called as bolt. So a topology can be thought of as a wiring up of spout and a lot of bolts. And these bolts are the ones which consume messages from their parent spout or bolts, and then they can emit tuples downstream. So this allows an application developer to define an arbitrarily sized graph of processing. Okay, so that's pretty much about Storm in a very, very simplified manner.
So from this nature, the spout and bolt topological nature, what are the big advantages that you get?
Right. So the first and foremost advantage which we could see when we actually went through the documentation and tried out a lot of sample applications is what we found is that for a beginner it was fairly easy to actually understand how to quickly onboard. So the entry barrier in terms of understanding the architecture and the overall design was not there. As a developer, if I understand what spout does, what a bolt does, and I just have a look at the interfaces, I can very quickly define and just get going. So to me, that is one of the biggest advantages which the architecture provides. There are other robust, strong points of their architecture. So, for example, the entire cluster is managed by the master daemon called Nimbus, and so essentially, Storm allows you to define a multi-node cluster where each node is managed by what is called a supervisor daemon, and the supervisor daemon is the one which spawns a lot of worker processes. These worker processes are the ones where the topology runs. Okay, so what it means is that if, as an enterprise, if I have some hardware resources available to me, if let's say I have a 10 node setup, I can very well spin off a Storm cluster and I can submit n number of topologies which would be submitted over there, and each topology can be configured to run on the specified number of workers. right? So Storm allows you to define the parallelism at various levels in your topology. So for example, you can say that, hey, I want to run this topology of, let's say, word count, which is the hello world equivalent, on, let's say, 4 workers. Storm will automatically figure out which boxes should those workers be spawned. Within each worker, again, if my topology has, let's say, a spout and, let's say, a word, a sentence decoding kind of a board, I can configure the parallelism in terms of how many executor threads should be spawned. And within each executor, I can again specify how many tasks of my bolts should be created. So Storm allows us to represent the parallelism at various levels. A, at the topology level; B, at spout and bolt level at initialization time; and more importantly, once the topology is submitted and starts running, it also allows us to scale out by simply throwing in more hardware and rebalancing the topology.
Okay, so now let's talk about Spark streaming. At a high level, how does Spark compare to the Storm architecture?
Right. So at a high level, Spark streaming is nothing but a wrapper on top of Spark. So what Spark streaming says is that let us try to define what they call as D stream, which is discretized stream. So essentially, if I have an input stream, what Spark streaming does is it breaks down the stream into smaller batches. Okay, and it passes on each input batch to the underlying Spark framework, and the Spark framework picks up the input batch, which it calls as RDD. RDD stands for Resilient Distributed Dataset, which is the core abstraction of Spark batch processing framework. Okay, so Spark streaming chops down the input stream into a lot of micro batches, where each batch is treated as a unique RDD by the underlying Spark framework. That creates an output RDD, and a sequence of these output RDDs is what comprises of an output D stream. So in a sense, Spark streaming is a stream processing system which is built on top of the core batch processing framework, right? That's all. If you really want to look at Spark streaming from a 30,000 feet.
So I know that you wanted to get away from micro batching. That was at the root of our introductory discussion.
Right.
So was that one of the biggest downsides that you were looking at when you were thinking about Spark?
Okay, so actually, we actually came up with a lot of evaluation criterias, and we said that, hey, we want to look at both Storm and Spark streaming. How do they fare on each criteria? So first of all, we said let's see what all kind of use cases we have at InMobi, and we found that there were actually a lot of applications which didn't want to wait for order of seconds. They actually wanted to process their data as fast as possible, period. So for those kind of applications, Spark streaming wasn't naturally the best fit. It was still possible to go ahead with Spark streaming, but that would have meant compromising some subset of use cases for the other subset. So that was so the micro batching was one of the aspects which probably did not go in favor of Spark streaming for us. But having said that, there are a lot of other use cases where, as we said in the beginning, they were simplifying Spark streaming. So that meant that we had to actually, go and look beyond the micro batching itself and try to evaluate on other criteria as well.
Over Thanksgiving, I had a great idea for a web app. So instead of spending time with my family, I locked myself in a room and I started building this application using Express.js because I love full stack JavaScript. So I was testing my application locally and I was making great progress. So I decided to deploy it and share it with some of my friends and get some feedback. I used DigitalOcean. I signed up for an account using promo code SEDaily, and in 15 minutes, I had my app deployed to a server and running. It was that simple. This was really the first time I had used DigitalOcean. So if you're like me and you like building stuff and you have ideas for projects, give DigitalOcean a shot. It is the fastest and simplest way to deploy an application that I've ever used. If you want to give it a try, go to DigitalOcean.com and use the promo code SEDaily to get $10 in free credits. Check it out. So I know that some people, when they have different application requirements across their stack in terms of the time sensitivity for their data, they go with like a Lambda architecture. Mm-hmm. Did you look at the Lambda architecture at all as a way that you were going to be architecting your system?
Right. So Lambda architecture is getting a lot of traction these days, and it's actually more of a buzzword if you really ask, because what it means is that if you are getting a lot of data as your input, you want to have both stream processing as well as batch processing trying to work on the very same input, and both generating different views simultaneously, wherein batch processing may just want to look at data at a daily level or at an hourly level, whereas the stream processing may want to pick up the data of the current hour by which time your batch processing hasn't kicked in, and then you have a layer which tries to unify the output of both your stream processing and batch processing. So when we actually started summarizing our use cases, we couldn't really find a lot of such use cases at this point of time. So we would want to build some applications which want to be based on Lambda architecture at some point of time, but then we didn't want to base our platform choice on a future requirement as simple as that. So we just thought of solving the use cases which would be like more prominent.
Right. And so those use cases are outlined in these evaluation criteria which you considered.
Right.
So we should go through some of those evaluation criteria. So you're looking at Spark streaming and Storm, and you're trying to decide. And so the first evaluation criteria is the processing model. And you've already kind of outlined the different processing models of Spark streaming and Storm.
Right.
Storm is these spouts and bolts that compose topologies. And Spark streaming is this resilient distributed data set pipeline. So how do these compare? It sounds like Storm at least wins out on simplicity and ease of use. What were the other?
Right. So in Storm, actually, it's as simple as that. As soon as a message is picked up by the spout and handed over to the board, it immediately gets processed. Whereas in Spark streaming, the message has to wait for what's called as the batch interval. So Spark streaming documentation says that you can configure your batch interval to as low as half second. But then practically speaking, when you start tuning your application beyond initial hello world kind of applications, and you start thinking of how to deploy them, very soon you uncover that trying to reduce the batch interval leads to a lot of jobs which are getting submitted to the Spark driver. Okay, which creates a lot of pressure, because what it would mean is that the entire processing has to be done within that very time interval. Otherwise, you are going to have backlog. On the other hand, if you increase the batch interval to say 5 seconds or 10 seconds, you might get better throughput, but then at the cost of latency. So we actually just went to the horse's mouth. We actually checked out the documentation and a lot of resources from the authors, and they themselves try to caution that the tuning of batch interval has to be done carefully, so as to make sure that the steady state is achieved. So there is a bit of a caution advised while tuning the batch interval, whereas similar thing doesn't really exist in Storm.
Got it. So what about message delivery guarantees and fault tolerance? You compared Storm and Spark on this axis of message delivery guarantees and fault tolerance. How do they compare?
Right. So actually, that's a very important ask. Message delivery guarantees, because some applications. So let's try to define what's a message delivery guarantee really mean. So some applications would want what's called an at least once guarantee, that it's fine if you process a message more than once, but you have to process at least once. So in other words, application is saying, I'm fine with data duplication, but don't drop the message, don't have data loss. There could be second class of application which would want at most once guarantee. They would say, don't duplicate the data, don't duplicate the message, okay? Just pass the same message at most once. And then there's a third class of application which says, I want each message to be processed exactly once, which means neither data loss nor data duplication. Now, there are different applications which would want different kind of guarantees. For example, let's take a very simple example. If you have a billing kind of an application, you want an exactly once. You don't want to overcharge somebody, nor you want to lose money on the table. Okay. Now, at least once. So if you are doing some kind of analytics where you want to capture the trend of what's happening in a particular geography for a particular set of customers, you might want to have at least once for some class of customers, or you may want at most once for other class of customers. So there is a lot of mix and match in terms of the asks. Now, coming to the technology platforms, Storm actually has two layers. One is the core Storm, which talks in terms of spouts, bolts, and topologies. And then they have defined a high level programmatic framework, which is called as Trident. Right. So what we found is that the core Storm, it actually guarantees at least once processing natively, which means that each message, as soon as it's picked up by the spout, it hands over to the bolt, and then there is something called a message timeout. If the message is not acknowledged back by the spout within that timeout, the message is marked as failed, and it's simply pushed back down the pipeline. So it easily is able to achieve at least once. At the same time, the processing framework allows you to bypass the hacking, which means an application can do at most once as well. Now what's left is exactly once. Exactly once requires an at least once at the source, which is there, and the target bolts have to have the capability of deduplicating the messages. Okay, so what it means is that if the external system where the bolt is trying to write data, if that supports a capability of identifying that given a message, have I written it already or have I seen it already? If yes, let me drop it. If this kind of capability is natively available is provided by the external system. For example, uh, a key value store, or let's say relational system, right? So you can very easily achieve exactly once in Storm. So overall, uh, the rules of the game are quite nicely laid out by Storm. If you look at the Trident, the documentation really goes in detail and tries to define uh, how to really write a transactional spout and a transactional state which can achieve all these three message processing guarantees. And obviously the same knowledge. How does Spark streaming fare in this area? So what we find is that Spark streaming tries to define this entire story in terms of how is my receiver from which I'm reading message, how is that guy, is it reliable, or is it really capable of handling acknowledgements. And if it is, the Spark streaming architecture allows you to read the data in by what's called as receivers. Those receivers hold the data for the current batch, and they replicate amongst themselves, and then the Spark job gets triggered. Now, what we found is that the early versions of Spark had scenarios of data loss happening. For example, if your Spark driver got killed in between, or let's say your receivers read the data from the external source, uh, they got data in memory, but they died in between. There were some scenarios where you could have loss of data, which was fixed by Spark streaming in the subsequent versions. I think in 1.2, or they introduce write ahead logs. So what that meant is that the network receivers would read the data and immediately write it to SDFS, so that before actually handing it down for processing, so that in the eventuality of receivers going down, when the job is again triggered, the data is read from the write ahead log. So this actually provided fault tolerance to some extent, but then what it also meant is that there is a lot of overhead in terms of unnecessary replications happening. There's a requirement for spinning up an SDFS cluster simply for doing SD write ahead logging, and overall it was quite inefficient. It also meant that I have to, as an administrator, as an operational guy, I have to really worry about spinning off extra nodes, extra storage, simply to hold the redundant data, which can be useful in terms of in the cases of data, in cases of let's say your daemons going down. So but the good thing about Spark streaming is that the community is really working, reacting very quickly and solving all these bottlenecks. For example, they have given a lot of special attention to Kafka as the source, and they've provided a direct integration APIs for Kafka specifically, I think in release 1.3, which was the latest release at the time of our evaluation.
So it sounds like the trade-offs are made even more complex because if you choose Spark, it sounds like Spark may not have been the best. When you were doing this evaluation, you were kind of thinking, well, Storm looks stronger, but the Spark community might be stronger, so exactly. Spark might win out over time.
Right, exactly. So Spark streaming, by design, they don't have a true native stream processing framework. They are trying to achieve stream processing by shrinking the batch and allowing people to configure as small a batch size as possible. But the underlying processing framework, because of the way it's designed, it actually ended up reading data but having some data failure scenarios, which they are trying to very quickly fix on a case-to-case basis. For example, for Kafka, they have given direct integration where they've just bypassed the executor layer. The job directly reads from Kafka and tracks the offsets at each Kafka partition, and it's able to achieve exactly one semantics. But then what it meant for us is that there are a lot of other proprietary messaging systems within InMobi, and which might well be the case with other enterprise companies as well, where you can't always assume that your data, your source systems would always, in 100% scenarios, will be having data always available in Kafka. If it is not the case, then you might be running into suboptimal scenarios with Spark streaming, which was actually the case with us to begin with.
But even in that scenario, couldn't you hand off the data from the ingesting message system to Kafka?
Right.
And just have Kafka as the universal point of integration?
Right. That's always an option available. But what it meant is that in order to work around some inherent limitation of the stream processing platform, I would have to actually ask for more resources to pick up data from one system and ingest data in another system. It is possible theoretically, but then it could be like costly in terms of operational requirements. Somebody has to really monitor those very pipelines, which have to again be designed in a robust, fail-safe manner, providing all sorts of data consistency and fault tolerance guarantees. So
Yeah.
as you can very well see, building layer on top of another system brings up a lot of overheads, both in terms of manual resources and also operational overhead, which we clearly wanted to avoid. But having said that, what we are finding is that Spark's community is very rapidly evolving, and for example, the Kafka direct integration mechanism is being extended to other important sources like Flume, and there are others. So we do foresee that in the near short to medium term, they would be trying to overcome these limitations to some extent.
And one of the other evaluative criteria you were looking at was automatic scalability.
Right.
How did Spark and Storm compare in terms of automatic scalability?
That's a very, very important requirement, because we are living in a world where the input traffic simply can't be thought well in time. You can have overnight spikes of data. You have a product launch, it goes viral, and all of a sudden you have 10x of the data which you have to process. Or let's say you have your downtime happening in your processing pipeline, resulting in a backlog. You are stuck for hours, and then as soon as the downstream systems they come back online, you are left with processing huge amount of backlog, which you have to quickly clear in as less time as possible. So the whole story of AWS cloud is simply around automatically scaling, right? So that was clearly one of the asks from Storm or Stream or Spark Streaming or any other candidate. Hadoop does very well in this area. What we found is that Storm actually had added the capability of automatically scaling by providing a rebalancing capability. So what that meant is that initially, if you have configured your cluster with, let's say, 10 nodes, you have let's say you have saturated the resources. If you have a lot of new incoming data and you have spare hardware, all you need to do is to spin up the new boxes, run supervisor daemons on them, and configure them to point to the zookeeper cluster. That's it. Each supervisor daemon is intelligent enough to join the cluster and declare its resources to the overall cluster. As once that is done, an administrator can simply issue a rebalance API where they can increase the parallelism of currently written topologies, and Nimbus would automatically scale out the tasks running on the older boxes out onto the newer boxes. So that allows us to scale out and scale in as per our requirements. On the other hand, when we look at the Spark streaming, they actually did not support automatic scaling at that point of time. We checked out the mailing lists, and it looked like, because Spark streaming is underlying using Spark framework, Spark assumes that at the starting of the job there are these n number of tasks, n number of executor processes which can't be compromised during the course of that run. So what it means is that if I have 10 executors participating in the current instance of the job, those 10 have to be there for the job. They can't be increased or decreased during the run of that job. And that sounded like a big enough limitation that probably deserved a deeper look, which might have taken time to be fixed by the Spark streaming community. They might need support from the underlying Spark framework itself to be able to achieve automatic scaling, and hopefully they should be able to solve that sometime in the near future as well.
So we've explored all these different evaluation criteria. Let's talk about what you chose. What platform did you end up using?
Right. So overall, when we actually put up our evaluation criteria and when we try to summarize putting both platforms side by side, we actually had very interesting observations. What we found is that Storm were doing quite good in some areas. For example, the processing model was simply very broad enough to handle both per message and batch, and then the message delivery guarantees was simply complete from our requirement perspective. The fault tolerance was very good, as in you kill any supervisor, you kill any Nimbus, and it has absolutely no impact on the running jobs. That's exactly what we want. The auto scaling was one of the strong points, but then there were some weak points in Storm as well at that time. For example, the state management was not as good as what we would have wanted. Some teams would want very rich windowing capabilities. For example, they wanted to maintain states for a long period of time and consult the states during the course of the processing. So Storm was not faring that well in this particular area. The Yarn integration was not up to the mark at that point of time, because we tried integrating Storm in Yarn via slider framework. Now that did allow Storm to join the Yarn cluster, but then there were some very apparent limitations with respect to how to debug. The log files were simply not reachable. We had to log into boxes, find out where they are, and it was really a very painful exercise. On the other hand, Spark streaming had its own strengths. For example, Yarn integration was simply there because it's meant to support mesos in Yarn from day one, and Yarn gives it a capability of resource isolations, because in Yarn you can really configure your C groups to lock down the number of cores each container would take, even the memory requirements. So that caters very good for Spark streaming. The functional primitives which Spark streaming provides are really pretty rich for anybody who wants to do rich ETL capabilities. But then the core platform pieces, some of the critical ones were missing. For example, the fault tolerance was not really up to the mark how we would have liked it. The message delivery guarantees are being fixed on a case by case basis, for example, for Kafka, but then it's not really a 360-degree offering as it stands today. So overall, putting everything into perspective, we felt that probably we should standardize for Storm as the choice of our platform to begin with, and start developing applications on Storm.
Have you finished building out your Storm implementation?
Right. So as we are speaking, we are actually productionizing a lot of our processing on Storm platform, and we are actually seeing pretty good results so far.
What kind of results are you seeing? Is there any? Can you contrast any sort of performance metrics with how things were prior to implementing a streaming framework?
Okay, so actually, prior to going Storm, we really didn't have any true stream processing platform, and neither we had applications which were doing real-time stream processing, except a few proprietary applications which were really implemented for solving a very small subset of use cases. So in that sense, it has been a very novel exercise for us, and quite exhaustive as well, because we are really ambitious. What we want to do is to actually consume the entire activity streams which are being generated geographically in our various clusters, and we want to build topologies and deploy them in our geo-distributed setup in such a way that we are able to process each and every message in sub-seconds latency. So the initial results seem to be indicating that it is indeed possible to get closer to those latency targets. So we are also trying to have a very keen eye on where the Storm community is going. Of late, there has been a lot of traction, and a lot of exciting features are being added in Storm community as well, which really are important for any enterprise. For example, they're adding security and Nimbus high availability, and capability to have back pressures in case of processing going slow. So these are some of the very key requirements which gain immense value when you start operationalizing beyond development. When you're actually running the show, these things do become very important.
That's great. Well, to begin to close off, I guess I'll ask you one final question. What do you see as the future of the big data stack? Like, how do you think these different streaming platforms will evolve? So I was just at QCon, which is this conference in San Francisco.
Right.
Well, they have conferences all over the world, but this one was in San Francisco, and there were all these talks on streaming frameworks. There were so many of them. Like,
right.
I think it was a single day, and I heard about like 10 or 15 different streaming frameworks. How does this stuff get resolved? I mean, we used to just have Hadoop, and it was like everybody just used Hadoop.
Right.
And
So stream processing is actually getting this entire space is getting very interesting, because of late there have been a lot of new players. On one hand, you have fairly established frameworks like Storm, which have been out there for a long time, have been really proved in real battle testing scenarios, handling internet scale data at Twitter and Yahoo. On the other hand, you have like Spark Streaming, which is backed by a rock solid community, adding a lot of features on a day-to-day basis. And then on the other hand, you see all these new players like Apache Flink and Apache Apex, which is the data torrent, open sourcing their real-time stream processing engine. So we are really entering in a world of stream processing where there's going to be a lot of mix of these players. So it looks to me that stream processing is something which is here to stay. Number one, there's no doubt about that. The processing requirements, the latency asks are reducing day by day, and it's very obvious. You as a customer, if you're using any application, nobody has the time and energy and patience to wait for your results to just come just buffering. So nobody is going to do that. So there's a lot of pressure on the enterprises to be as fast and agile as possible. So the way we foresee is that each framework is going to bring a different set of strengths, which would might be meaningful to a different class of customers. So, for example, if somebody wants to get very low latency processing and very simple operational deployment, they might want to go Storm. On the other hand, if somebody wants to write a same code base which works in batch and streaming, and they want to achieve Lambda architecture, they might want to go Spark Streaming. On the other hand, if somebody wants to have your DSL kind of requirements which Flink is giving, they might be inclined to Flink. So it's going to be an interesting mix, but we still need to see in the long run how much of community and how much of industry adoption is there, because at the end of the day, these are the single two most important things which define and determine the success of any platform. You have to have community backing the project, and you have to have large scale deployments where issues are getting ironed out. So we have to wait and watch to see how the space gets matured and more clarity is there.
Great. Well, Satish Mittal, thank you so much for all your time. This has been a really interesting discussion. You've answered a lot of my questions around these different streaming frameworks and how they trade off and why there's so many of them. I look forward to more blog posts about InMobi and how your streaming architecture progresses.
Right. We will definitely be sharing our learnings and insights which we are getting as we progress on our journey.
Awesome. Well, Satish, thanks for coming on to Software Engineering Daily.
Thanks, Jeff. It's been great talking to you. My pleasure.